Okay, today we'll be talking about the torsional deformation. Actually, there are two types of torsional deformation. The first one is the Saint-Venant torsion. The deformation caused by Saint-Venant torsion. And we have also the warping torsion. And the deformation caused by the warping torsion. But here we will mainly talk about the Saint-Venant torsion and the torsional deformation due to that. This is what we have seen in the strength of materials class. Warping torsion is a different, it not only causes shear deformation, but at the same time it bends, it warps the structure. We mainly talk about this thing in steel design courses, but in terms of formulation, this is more complicated and this is a more advanced topic, which we will not discuss it in this class. That you should be aware of it, especially when you work on steel structures. But mainly our main focus today will be the Saint-Venant torsion and related deformations. So we say that the Saint-Venant torsion will create shear deformations, and we will try to figure out equations that describe that deformation due to Saint-Venant torsion. In order to see pure Saint-Venant torsional deformation, we should have a circular section. So we will use that circular section to derive our equations. So let's say that that's the center. And let's assume that I apply torsion to this. And the length of this member is L, okay? This end of the member is fixed, cannot deform, but let's say that this end is free. So what do we see? Let's say that I have this point, okay, it was initially here. When I applied torsion, so it moved to that point, okay? So initially it was here, it moved to that point, and we see a angle of twist. That's the way this structure deforms. So I will just try to figure out the strain deformation relationship. And then we will relate the stress with the applied torsion, and then I will combine these two. So that point was initially here, okay? And since this end is fixed, this point didn't move, but it was here in this fiber, in the same fiber, but this thing moved here. So I should have a deformation like that. So let's draw that deformation also. So this type of deformation will cause only angle change. So that's the angle change. It was initially 0, but when I apply the torsion, I see an angle change. And by definition, this is my shear strain. So my aim here is to relate the shear strain with the corresponding deformation, which is the angle of twist. And in order to relate it, I can use the length of this arc. If I assume small deformations, so for small deformations, we can write the following relationship. If I assume that the radius is equal to C, I just name it as C. So this arc is equal to angle multiplied by the length. In other words, shear strain multiplied by the length. That's equal to angle of twist multiplied by the length of the radius, which is equal to C. And that's equal to C times theta. Now, in that case, my shear strain is equal to angle of twist multiplied by the radius divided by the length of the member. Now, the second step is to relate the stresses with the applied loading. So, stress applied loading relationship. In that case, it will be torsion. So let's take a circle again. That radius is the length of that radius. We said that it's C, and that will be the coordinate axis of, let's call it R. Okay, and we are assuming that this torsion will create a linear stress distribution. At this member, and this stress is tau max, and the variation of that stress, or the stress anywhere on this triangle, is equal to shear stress R is equal to shear stress, maximum shear stress tau max divided by the radius times R. Okay. Now, in order to relate this applied torsion with these stresses, I have to calculate the torsion created by each stress component. So the torsion created by this maximum shear stress at this location is equal to shear multiplied by the radius, this distance to the center. So I have to do it for every stress and then add it. Okay. So we show it this way. Torsion is equal to, I'm adding the torsion of every stress, every piece at the, or every infinitesimal area. And at the infinitesimal area, I have the shear stress tau R, and the distance of the infinitesimal area to the center is R, and I added all the infinitesimals area, dA. Okay, so remember that this is the shear force on an infinitesimal area. Shear force multiplied by its distance to the center give me the torsion due to at that small infinitesimal area. Now I'm adding it all the infinitesimal areas and I get the applied torsion. Now let's put this equation into that integral. Then we will have the following: integral tau max divided by the radius times r square dA. So I just write it in this form: tau max divided by c r square di. So this is a property that we know, right? That's a sectional property. So this is the second moment of infinitesimal areas with respect to the center. But here we are using the polar coordinate systems to locate a point, right? If I have a point, the way I locate it is using the radius and the angle. So this is a moment, second moment of the area, second moment of the areas written in polar coordinate system. So we call this one as polar moment of inertia. and we show it by J. So put that J into that equation, I end up with the following relationship. The maximum shear stress at the circular section is equal to torsion multiplied by the radius divided by the polar moment of inertia. This is for the maximum stress, but I can write it this way. The shear stress at any point is equal to torsion multiplied by the distance of that point to the center, which is the radius, divided by J. And that's the stress applied loading relationship. And here I have the strain deformation relationship. Now I need to write the stress strain relationship. Which is again we are using the Hooke's law. Shear stress is equal to shear modulus multiplied by the shear strain. Now put this into that equation, put the stress again into the similar equation, and at the end of the day we'll get the following relationship. Torsion is equal to G shear modulus polar moment of inertia divided by length multiplied by the rotation. And that's the relationship that we are looking for, which is the applied force deformation relationship. And it has a similar form when you compare with the previous equations that we derive. I have the applied force here, material property, sectional property, and member property. Remember that if we write it for axial deformation, here I have P is equal to material property, section property divided by the member property multiplied by the deformation, and that's the same form. Now the other thing that we assumed here is this is a torsional deformation due to San Venant, and it's uncoupled from the bending deformation and shear deformation, axial deformation. We are assuming that the torsional deformations occur independently. So in other words, it doesn't matter the magnitude of the shear deformations in your structure. It doesn't influence your torsional deformations. You will always have this relationship. How can we write this, or how can we assume it? Because we are saying that all deformations are small. The bend or one deformation type doesn't influence the other deformation type. Okay. Now we derived the applied force deformation relationship, and from that we can actually derive the stiffness coefficients for a member. Let's do that. Stiffness coefficients. Again, we will use the first principle like we always do. That's my member I, J. I'm just driving it for torsional behavior. So at this end, I have an angle of twist. That's my first degrees of freedom. And at the end node, I have another angle of twist. That's my second degrees of freedom. And the torsional deformations are coupled from the bending and the axial deformations. So I got only 2 degrees of freedoms. Now let's work on case 1. Where d1 is equal to 1, and d2 is equal to 0. So what I will do is I will apply K11 to create a unit angle of twist. Let's show it this way. That's equal to 1, and the angle of twist at this point is equal to 0. So the moment or the torsion that's required to create that angle of twist is equal to G times J divided by L. And here on the other side, I should have the same angle of twist, but in the opposite direction. G times J divided by L. And that's the node. And at the node, I should have K21 to keep the angle of twist equal to 0. So that's the moment here. That's the moment here. So the first row, if I write equilibrium at the start node, I obtain K11 as equal to G times J divided by L, and K21 as equal to minus G times J divided by L. You can write the same equation or repeat the same procedure for case 2, and when you do that, at the end of the day, the stiffness matrix will be this: Gj over L minus Gj over L, and that's the element stiffness matrix that shows the torsional behavior. Since torsion are uncoupled from the axial deformation and bending deformation, we can just add these coefficients to the element stiffness matrix. Okay, we talked about all the deformations type. Now let's derive or generate the stiffness matrix of a 3D space frame element. Space frame member. And while doing that, I will be ignoring the shear deformation. So the type of the member, it will be a Bernoulli Euler frame member. So when you hear the word Bernoulli Euler, you will directly understand that there is no shear deformation in this member. So let's draw our member. Let's show the degrees of freedoms. Now for this time, this is a 3D-dimensional problem. At every node we have 3 degrees of freedoms. So this is D1. That's D2. And this will be D3. Now the rotations in the element along the element axis will be D4. This will be D5, and that will be D6. So at the start node we have 3 degrees of freedoms, 3 translational degrees of freedom, and 3 rotational degrees of freedoms. Let's continue. So we have 6 degrees of freedom here. This will be D7, translation at the end node, D8, D9, and we have the rotational degrees of freedoms, D10, D11, and D12. So basically we have 12 degrees of freedom in the system. Now we have to talk about the local axis. So let me draw a smaller 3D version of that beam element. So let's say that it has a rectangular section. So usually the element axis, it's the center, is called as the x-axis. And then we'll have y-axis and z-axis. And we usually use the right-hand rule to determine the y or z-axis. Let me draw the section now. That's the rectangular section. So that will be the y-axis, and that will be the z-axis for this member. Now let's think. Now d6. Now the translations are straightforward, but let's see what kind of rotation does d6 create. So it will be the rotation along z-axis, right? We put our right thumb along the z-axis, and that's the rotations that d6 create, and d5 will create the rotations along the y-axis. So if we just name it as the rotation, let me draw it here. So the rotation along z-axis will be rotation along the strong axis of this member, right? If we just assume as a rectangle, so we will better understand. So rotation z is this rotations along the z-axis, and rotations along the y-axis is this type of rotation. So it bends this rectangular section along the weak axis. Now remember, when we do a 2D version of this element, we were looking at this member from this side, right? We have translations in D1, we have translations in D2, and we had rotation in D6. So this is what we were doing when we analyze the structure in 2 dimensions. Now we add another dimension, and we have a weak axis bending, right? The weak axis bending is due to D3 and D5, and here D4 will create a torsional deformation. Now let's take a look at the stiffness coefficient. Of course, I'm not going to draw all the stiffness coefficients, but I'll just do it for the weak axis bending. Okay, now if you think about it, we already derived the torsional stiffness coefficients. In 2D members, we already derived the stiffness coefficients. D1 will be axial, D2 and D6 will be bending along the strong axis. Now I will just discuss case 3, bending along the weak axis. The logic is exactly the same. The only difference is I will draw the structure in 3D. This is the member, that's the end node. Okay, let's put the forces. Let me mention that I'm working on case 3 now. So we got D3 is equal to 1, rest is equal to 0. I'll say D12 is equal to 0. So I apply K33, right? The K33 will create a unit translation in the Z direction, all right? And I have to apply K53. K53 will keep the rotation in the Y direction equal to 0. So I have K99 will keep the translation at the end node equal to 0. And I should have K11 3, sorry, this shouldn't be K99, right? It should be K93. Now K11.3 will keep the rotations at the end node in the y direction equal to 0. So the deformed shape that I will see is something like that. The translation is in the z direction, the rotation is in the y direction. Okay, so how much force do I need to create this unit translation? Again, we will use the slope deflection equation, right? But since this times all the bending are along the weak axis, I will use 12 EIY divided by L cubed. And for in equilibrium, this force should be 12 EIY L cubed. And the moments, so I should have a moment in this direction. Maybe I should show that this moment is, let me try to draw it in a better way. This is difficult to show in 2 dimensions and on a 2-dimensional paper. Let me show the axis first. So I'm applying a moment in this direction and the magnitude of that moment is 6 EIY divided by L square, and here the moment again will be along the y-axis and it's in this direction, and the magnitude is 6 EIY divided by L square. So when we write the stiffness coefficients, we obtain K33 as equal to 12 EIY divided by L cubed. K53 is equal to minus 6 EIY divided by L squared. K93 is minus 12 EIY divided by L cubed, and K11.3 is minus 6 EIY divided by L squared. So let's repeat. The only difference of a 3D space frame from the 2D version is we have bending in 2 directions, right? In the 2D version, we only discussed or considered the bending along the strong axis or the bending along the z direction. In other words, when we worked on the 2D version of this member, we were looking at the member from this side and we were seeing axial deformations, D1, vertical or the translation along y-axis and rotation along z-axis. Now when we take a look at this member in 3 dimensions, so we have another bending, which is the bending along the weak axis. And if you think about it, we should have the same equation that describes the bending along the weak axis. And again, since we are assuming small deformations, linear elastic material, we are investigating the bending along the strong axis and bending along the weak axis as if they are independent from each other. Okay, they are not coupled. The strong axis bending doesn't change anything in the weak axis bending. Okay, so that's the bending part. We also have the rotations along the element axis, rotations along this direction. That's what we called torsion. We derive the torsional stiffness coefficients, and since they are uncoupled from the bending along both directions, we don't have to combine it with anything. It's just very similar to the behavior of the axial deformation. The only thing that we have to be careful here is which moment of inertia that we are going to use to describe the bending stiffness. So if you think about it, since this will in the y direction, in the weak axis direction, that's the way the moment is, the direction of the moment. So we should consider the moment of inertia defined along y-axis. So that's why I say IY. When we have the strong axis moment, we have to consider the moment of inertia defined in the z-axis. Okay, so that's the only thing that we have to be careful. So the element stiffness matrix, remember this is the element stiffness matrix in local coordinate system. You already have these matrices in your notes. These are the local coordinate systems, of course, that we have to consider. We have to think about how we are going to rotate it. And this is another topic that we will discuss. But let's right now focus on the derivation of this member. So this is this 12 by 12 matrix. That's the coefficient for axial deformation. That's the stiffness coefficient for torsional behavior. We didn't call this Ix, but we said it's J. It's the same thing. It's the polar moment of inertia. And here we have the coefficient for strong axis bending, right? And these are the coefficients for weak axis bending. I drive this row above, and you can repeat the same procedure to drive the other coefficients. And that's mainly it. There's nothing new here. The only difference is you have to be careful with the coordinate axis definitions. You have to be careful with which moment of inertia to use in which bending direction. These are the key issues when you have a 3D space frame. But other than that, all the coefficients that we have is derived in a similar manner. Now, you can have the 3D space frame for shear deformations also. So the only thing that you need to do is to replace these bending terms with the coefficients that involves the shear deformations.